All right, guys, let's look at 5.1, the natural base e. So it says natural base e is an irrational number. The other irrational numbers include like square root of 2, pi, that kind of thing. And we're going to use this natural base e with some exponent rules. So the exponent rules that we've got here, it's just a couple of them. If you are multiplying with the same base, you add the exponents. If we are doing the exact opposite, if we're dividing with the same base, then I subtract my exponents. Now subtraction order matters. I have to do the numerator first minus the exponent on my denominator second. All right, so let's do this with your base e. So these ones both have the same base and they're multiplied. So I think I'm gonna go with this multiplication rule here where I add the exponents. So I'm gonna have the same base here, e, and I'm going to add the exponents 3x plus 6. One of them has an x, the other does not. They are not like terms, so that's actually as good as it's going to get right there. On number 2, I'm probably going to use the division rule, where I should be having the same base. They were both an x. I'm not going to have an x necessarily. I've got an e as the same base. The 16 and the 4 don't have the same base, but I do know what 16 divided by 4 is. 16 divided by 4 is 4. And then I'm just going to look at the ones with the e to the third, divided by e to the fourth. I'm going to use this rule where I do the m, the numerator, minus the exponent in the denominator. So it looks like my numerator has an exponent of 3 minus the exponent in the denominator of 4, which 3 minus 4 is negative 1. And this is not considered the most simplified. Usually we have positive exponents to be simplified. So this actually, a negative exponent makes us do a reciprocal. So I will bring that down to the denominator with the e to the positive 1. And actually anything to an exponent of positive 1 is itself. So I can just say 4 over e. All right, and then number 3 here, I actually have a 3 and e to the negative 4x. It's all squared. So I'm going to, again, put that exponent, excuse me, on each of them, which squared means multiplied by itself. So if you want to do it this way, I could write it as 3e to the negative 4x times another 3e to the negative 4x, same thing. All right, so like I said, I could be like a 3 squared and like e to the negative 4x is all squared, like I had 2 of each of those. Either way, I should get the same thing. My 3 squared, my 3 times 3 here is 9. And my rule for multiplying with the same base, this guy up here, means I have to add the exponents. So I'm going to add a negative 4x and another negative 4x. So negative 4 is negative 8. I get a negative 8x. All right, now this does still mean I am not considered simplified until I get a positive exponent, which means I'm going to have 9 over e to a positive 8x. Notice the 9 did not have a negative exponent, so it did not move down to the denominator, just e to the negative 8x. The e was the only thing with a negative exponent. Okay, so then there's the natural base functions that we're going to look at on some graphs here. A function of the form y equals a e to the rx is called a natural base exponential function. We're going to look at 2 different cases where your a, again the a is in front here, if the a is greater than 0, actually in both of these cases the a is greater than 0, you've got some positive number out there. The part that's different is the r, again the r in the exponent right here. If that r is greater than 0, if you've got e to some positive number times x, then the function is exponential growth. Okay, so that means exponential growth. It'll be this type of shape where it is growing as you guys read left to right, right? So it'll go left to right, it'll be increasing, going up and up and up. If I have the r less than 0, again, still with the a greater than 0, that's the same on both these cases though. If your r is less than 0, like a negative up in my exponent, then that would be kind of my exponential decay. Again, if I read left to right, it is decaying, it's going down. It actually, both of these have an asymptote, a line that they get really close to but do not cross, and that is my x-axis on both of these. So notice that these curves do not cross. It did not come down below my x-axis. There's nothing down there. Okay, so your e to the positive x, r is greater than 0. E to the positive x is this guy, exponential growth. My e to the negative x, so my r is less than 0, it's a negative. That's my exponential decay, so it goes down, decreases. Okay, so let's see if we can apply that to some numbers, not all letters. On number 4, it says, tell whether each function represents exponential growth or exponential decay, and then graph it. So if I'm looking at exponential growth versus exponential decay, the difference was that r, that number that was multiplied by the x and the exponent here, whether it was greater than 0, like a positive, or less than 0, like a negative. And I think this is like a 1x up here, but my point is it's a positive. So I'm probably going to be in this exponential growth category. Okay, so let's write that part down. All right, so it should have this basic shape where, again, as I read left to right, it should be increasing, going up. This actually, let's get some points here. I'm just gonna do like an XY chart. Okay. So let's see, I'll try to plug in like a negative, this over a little bit. So 3 times e to the, maybe I'll plug in like a -1. Okay, messy. But I did a -1 in for my x, and I got this like 1.1 for my y. And for my xy chart here, plugged in a negative, got like a 1.1, about 1.1. So there we go, there's that point. Maybe I'll do a negative, we'll do a 0, a positive, this kind of thing here, see if I can get the shape, maybe even like a +2. All right, with 0, do the same thing here. I'm just plugging in a different x value of 0. All right, so that gives me straight up 3. I get 0.03, which on my graph is 0, 3 right there. I do need more than 2 points. It's not a straight line by any means. It should be a curve. So I'm going to keep this going. I'm going to do a +1 now. All right, so instead of e to the 0, I get e to the first. All right, 8.15, yada, yada. So around that's like an 8.2. Then these are estimates, but pretty dang close. 1, and then my 8.2, a little over 8. Okay, the 2 I think will be off the chart here. We'll check it out just to make sure, but if I substitute a 2 in for my x, oops, there we go. So yeah, that's a little off the chart, so I'm not gonna put that on my graph. I do know I got 3 points here. It's not exactly a straight line. If this was a straight line, it would have been going a little, wouldn't have curved at all, I should say. But like what I set up here is there should be an asymptote, a line that it does not cross the x-axis. So I'm gonna make this kind of curve through my points here. See if I can draw it all right. Curving through the points and not crossing the x-axis. It's really close, but does not cross. Okay, so there's my graph. Let's try this one, number 5. This one, I'm still kind of asking myself these questions that I have up here. The a should be greater than 0, which I think that, yeah, this is like a +1 for my a in front of the e. It's a positive, so both of these are true. But the r is what's multiplied by my x in the exponent. And in my case, I've got a -5 times the x. My r is a -0.5. All right, but it is less than 0. It's a negative number of some kind. So it's in this category, which means exponential decay. So it'll have this kind of graph. Once I graph it, I should see it decrease like this. But first things first, we had to figure out if it's exponential growth or decay. This one, exponential decay. All right, so again, I know the basic shape. Let's get some specific points though. kind of go through the same process here. Maybe I'll plug in like a negative, maybe 0, put some positive, something like that. See if we can get the basic shape here. So this one was e to the negative 0.5x, and I'm going to sub in, like I said, like maybe negative 2 for my x. All right, 2.7, yada, yada. I'll round this to 2.7. My x was negative 2. My y is negative 2, or positive 2.7. Almost a 3. Okay, so there's that first point. Let's try again here. I'm going to plug in a negative 1 instead of a negative 2. Okay, so it looks like 1.6. A positive 1.6 when my x was a negative 1. So again, x goes to the left by negative 1. 1.6 is like almost 1.5 kind of thing, a little more than 1.5. Okay, so there's that point. And again, I need to see the curve. I know this thing is supposed to curve. All right, so I'm going to try this with a 0. As of right now, the graph looks like a straight line or something like that. So I need to get some more points. All right, so this one hit the point 0, 1. I plugged in a 0 for my x. I got out a 1 for the y. 0, 1. All right, I'm starting to see the curve. Let's plug in a positive number. We had a couple negatives. We had 0. Let's plug in a positive. Maybe I'll plug in like positive 1. All right, so 0.606, yada, yada, a little more than a half. But again, it is a positive number. Plugged in a 1 for my x, and I got this. Okay, so at this point, I'm starting to see kind of that curve. It's still, just like up here, should not pass the x-axis. It's called an asymptote. Should not pass that asymptote. So I'm going to have a curve here. Oh, wow. Maybe I'll try again. Okay, and it gets really close, but does not cross. All right. So there's my curve on this one. There's my exponential decay. Again, as I go left to right, it is decreasing. All right, and now this one is a little different in that I did say that a had to be greater than 0 in both cases, the a being what's in front of my e to the x. This one has a negative in front of my e. So this actually is going to be a vertical reflection. So let's consider what it would be like without the negative. If I had a positive 0.5 e to the 2x, then this is a 2 right here. That's my r, and that 2, that r is greater than 0. That's true. So normally it would be exponential growth. It would look like this curve right here. But because you have this negative in front of your 0.5, that negative actually, it's not greater than 0. Both of those are out. So it actually, instead of exponential growth, it's going to give me a reflection. So it should be down here, which again, as I read left to right, it is going down and down and down. This should be actually exponential decay. It is decreasing. Okay, so let's write this. Let's see if that actually is what it looks like on the graph, though. It should still have an asymptote at 0. Should not cross that. I'm just thinking it's going to have a curve this way. All right, let's plot some points. So let's see, I've got a negative 0.5 e to the 2x. So let's plug in some numbers for our x. Maybe I'll plug in like a negative number. All right. So, oh, it is in the negative section here. It's a negative, almost negative 0.1, teeny tiny, like almost 0. When I plugged in negative 1, here's my negative 1 for x. Got a little below 0, barely at all. Okay. And then I'm going to plug in maybe like a 0. So everything else is the same, just the x value that I'm plugging in is a little different. Change that negative 1 to a 0. Okay, so that gave me a negative 0.5, so it's still pretty tiny. So let's see, I have 0.5, it's like between my 0 and 1 there. 0 and negative 1, I should say. Okay, so I plugged in a negative. I'm going to plug in, well, I plugged in a negative and a 0. Let's plug in a positive, so maybe like a positive 1. And that's negative 3.6945, yada, yada. So maybe like negative 3.7. So here's my 3, a little over 3.5 there, maybe 3.7. And like I said, that asymptote is still on my x-axis. So I'm starting to see the curve here. It should get really close, but not cross the x-axis, I should say. Good heavens. Okay. Doesn't cross that axis, and then it looks like it has a pretty sharp curve to hit those points. Okay, and this is the exponential decay we were going for. All right. So if you need to make yourself a note, go for it. That negative was a vertical reflection. If I didn't have that negative, it would have looked like vertical or like exponential growth. But they had that negative, reflected it down, so that's exponential decay. All right, this is reaching back to math 1. So you've got compound interest formulas. If it's compounded n times per year, you've got the first formula. If it's compounded continuously, you've got the second formula. So it says you and your friend each have accounts that earn annual interest compounded continuously. The balance A in dollars of your account after 2 years can be modeled by this equation right here. The graph shows the balance of your friend's account over time. So you can kind of see a graph of this equation, which I'm thinking that kind of looks like this format. It's kind of got just some P, some principal initial amount. You've got the E in there. This other one didn't have an E, so I think that one's out. And then raised to the RT, so my R is the 0.04 and the T there. Okay, so the graph shows the balance of your friend's account over time. Which account has a greater principal? Principal meaning this P right here, like this is what you start with. That's like what you deposit into the account. And I'm thinking on my equation, the P looks like a 4,500. And then at the very beginning, like at time 0, here's my number of years, right? So at time 0, it looks like this hits 4,000. So out of my 4,000 to my 4,500, I think 4,500 is greater. So which account has the greater principal? This one says, this one's your account. The graph was your friend's account. So your account, the equation here, that's the one with the 4,500 with the greater principal. So which account has the greater principal? Mine does. All right, the equation they gave us right here has a greater principal than the graph for the friend. All right, and then which has a greater balance after 10 years? Okay, so this one for my friend, let's see, I've got 8, 10, 12, it looks like they're counting by 2s here, so that would hit up here. It looks like it's a little over that line, so 6,000, 7,000, it's a little over 7,000. All right, and then let's see for my account. Again, mine is this equation they gave me. They didn't give me the graph. They gave me the equation for that. Let's see what happens in this equation. E to the 0.04 times t, which they were saying my t, my time number of years is 10 years. So put my 10 in there. All right, so that's 6,713. Okay, that seems to be less than the little over 7,000 bucks that we were talking about. So I think after 10 years, the friend's account, the graph here, is going to have more money. Okay. And then this last little bit right here, scientific notation. This will be on the homework. You have to do some number right here between 1 and 10. Notice it does not equal a 10. But it has to be between 1 and 10 times 10 to some nth exponent. So like, basically I moved the decimal over. This is like, let's see how many zeros I got here. It's like 15,300,000, like 0.0 if you want to put it that way. But because it's like, there's the decimal normally, I got to move the decimal over to where I get some number between 1 and 10. So if I move it over here, oh, that's not between 1 and 10. it going, keep it going. Oops. 1, 2, 3, 4, 5, 6. Okay, I'm at a 15.3. I've put the decimal there. It's 15 still isn't between 1 and 10. So I'm going to do it again. 1.53. Okay, 1.53, that actually is between 1 and 10. So 1.53. And then how many times did I move that decimal over? 1, 3, 4, 5, 6, 7. I moved it over 7 times. So 1.53 times 10 to the 7th. And we can check it out. 1.53 times 10 to the 7th should give me the number they gave me, which had how many zeros? 153, good. Then 1, 2, 3, 4, 5 zeros after that. 1, 2, 3, 4, 5 zeros. Yep, looks good. Okay. So this is my scientific notation, some number between 1 and 10 times 10 to an exponent. This one looks like if I move the decimal over once, twice, 3 times, this would give me like a 0.38, but that is actually still not between 1 and 10. That's less than 1. So I think I got to move it over one more time to get like a 3.8, which 3.8 is between the 1 and 10. All right, and then 10 to the, I moved it over 1, 2, 3, 4 times. And if I put 10 to the 4th, you can check it in your calculator, that's actually incorrect. The reason why is I need to move the decimal in a certain direction. I need to get this tiny number, I need to raise it 10 raised to the -4th, which moves my decimal in this direction. And we can check this out. 3.8 times 10 to the -4. Okay, so let's see, I should have, let's see if it'll, calculator's not working for me. Decimal form would be 0.00038. It would have 3 zeros. And then the 3.8, they were giving me, they actually kind of gave me my answer. They gave me the scientific notation, 3.8. And then this E in my calculator means times 10 to the -4. So it's actually kind of does give me my answer, but if I'm moving the decimal over to the right, I had to have a negative exponent. When I was moving my decimal over to the left, I had a positive exponent. All right, there we go.